Hello, my name is Robert Wright from the Hawaii Institute of Geophysics and Planetology, and today I'm going to be giving you a talk about a 6U CubeSat mission called HyTI, which stands for the Hyperspectral Thermal Imager. HyTI was funded by NASA's INVEST program in the fall of 2018, and the goal of this program is to, by March 2021, deliver a 6-unit CubeSat which will acquire high spectral and high spatial resolution long-wave thermal infrared imaging data from a 6-unit CubeSat. So I'll give you a talk about the mission today and the science objectives of the mission. So I'm presenting it. I'm the PI of the mission, but this is on behalf of the HyTI team, which is a very large number of people. And you can see the affiliations of many of those people at the bottom of this slide. So first of all, the goals of the mission. So INVEST is the INVEST program stands for In-Space Validation of Earth Science Technologies. So the purpose is to space validate innovative new technologies which might form the basis of future Earth science missions. So the goal of HyTI was to demonstrate how we can acquire high spectral, high spatial, and high signal-to-noise ratio long-wave infrared imaging data from a 6-unit CubeSat, and also demonstrate high-performance onboard computing to process the resulting data so that we can actually get it down. So the three key technologies were, first of all, a Fabric Pro long-wave infrared imaging interferometer, which we developed at Hawaii Institute of Geophysics and Planetology. That's at the top there. Secondly, the JPL barrier infrared detector, FPA, which is on the lower left. And then finally, a heterogeneous onboard computer, which has GPU, FPGA, and CPU capability. The data rate from this instrument is an imaging interferometer, so the data rate in terms of level 0 frames is rather high. We then do a lot of processing to co-register those frames and Fourier transform the resulting level 0 information to get to a level 1 calibrated spectral radiance product. There's no way we can get the whole level 0 data set down on time, so we're relying on doing this processing on board and basically not falling behind, so that we can download what we collect by the time we want to download more data, such that we don't have a backlog of files on the spacecraft. So why is this relevant? Why did NASA fund it? Well, Earth scientists have never had access to high spatial and high spectral resolution long-wave infrared image data from Earth orbit before. So we've had Landsat, which has 1 or 2 bands. We've had ASTER, which has 5 bands. We've run out of EcoStress, which is in the ISS, which gives us another 5 bands. But never really high spectral resolution data. So on the left here, you can see the long-wave spectra of sulfur dioxide, volcanic ash, and carbon dioxide, 3 things which come out of volcanoes. Now with 2 bands, so I plotted on the top there the ASTER Landsat band passes. So you can see with those bands, we really don't have much leverage for example, discriminating carbon dioxide from sulfur dioxide or sulfur dioxide from ash, or any of those things from regular water clouds. HyTI is going to provide 25 spectral samples between 8 and 11 microns. So it will give us plenty of spectral resolution to not only distinguish these things in the atmosphere, but also enough spectral resolution and high enough signal-to-noise ratio to actually do some retrievals. So, for example, not just detect sulfur dioxide, but actually work out the amount of sulfur dioxide which is in the atmosphere at the time that the spacecraft goes overhead. So the measurement approach, HyTI is going to fly an imaging interferometer. So rather than using filters or a grating to split the light, we use the following approach. So in the top left here, you can see 1 frame of HyTI-like data. So there's a lump of quartz there in the first frame on the left-hand side. That's a single frame of data. So you can see those stripes on the right-hand side, which are basically the interference pattern, which is generated by the Fabric Pro interferometer. So that lies in front of the focal plane array. Light from the telescope passes through that before it's sampled at the detector array, and a single frame looks like it does right there. Now what you see here is light from each seen element sampled at a different optical path difference as we move from left to right or right to left. So the big black stripe on the right-hand side is basically the contacted region of this interferometer, which is 2 pieces of germanium glued together with a sloped air gap. So in this case, the air gap is like that. At the contacted region, there's no modulation, so we see that brown, that dark gray stripe. As we move away from that, so from right to left, then the optical retardation increases linearly as we move in that direction, as light, which bounces around in the cavity, suffers a different optical retardation or follows a different path length by the time it recombines on the opposite side of the interferometer in its sample at the focal plane array. So a single frame like that on the left gives us light from each scene element in each column modulated at a particular optical path difference. So a single frame doesn't really encode much spectral information. But if we translate that pattern to the right, so in a push-broom manner, so you can see here from T0, T1, T2, then light from each scene element is sampled at each successive optical path difference. At the end of this process, so there's an image on the right which shows this process taking place over the island of Hawaii. At the end of a collection of scenes, we then backslide each of those frames. And then at the end of that, we can drill down through each pixel in this cube and retrieve an interferogram for each scene element, which we can then just process to a calibrated radiant spectrum using standard Fourier transform processing. So that's how we acquired the data. This is the imaging spectrometer. So we're going to use an IDCA. We didn't have time to develop a custom approach for this. So this is a kind of standard off-the-shelf type implementation. Where we have just an IDCA window, cold shield. The FPA is located directly behind the interferometer in this picture. And on the right-hand side, we're going to use a refractive optic, which is everything sized to give us a 60-meter IFOV from an ISS type altitude of 400 kilometers. And we have a focus motor so that we can stay in focus. We don't have athermal optics. And the IDCA, all of this is on an optical bench, and then finally the heat sink, which I'll talk about later, which is an important component of the design. Next slide. So what will the data look like? So here's just some simulations. So we're going to have a 60-meter ground sample size. So on the left, this is a resampled Landsat image of the Big Island of Hawaii. 60 meters, you can see the lava lake as it used to exist a few years ago on Hawaii in that photograph. It's a push-broom imager, so the swath is about 20 kilometers. The inner graphic there, we're going to have 25 bands between 8 and 10.7 microns with HyTI. For comparison, ASTER, which is 20 years old, but still rather the state of the art for long-wave, high-ish resolution imaging of the Earth's surface and atmosphere, only has 3 bands at 90 meters over the same bandpass. Now, in terms of signal-to-noise ratio or precision, on the right, I show the NEDTs of predicted from our performance model, and basically, we're even in these narrow bands, which are 13 wave numbers, so 25 bands between 8 and 10.5 microns, we are predicted to exceed the Landsat Sustainable Land Imaging T requirement of 0.35 Kelvin in terms of NEDT. So the data will be high spatial resolution, high spectral resolution, and also rather high precision. So here's just an example of some data which were acquired by a prototype HyTI sensor. So in the left-hand side, you can see it in the gimbal there. Beneath it, you can see the gimbal attached to the aircraft. And then on the right-hand side is just a 9-micron radiance image, and then just some standard spectral matching algorithm performance results from the data themselves, where you can see we match clays and then gravels with the characteristic absorption features of those materials on the right-hand side. So these are some test data. The HyTI instrument will be, apart from adaptations for the relevant space environment, will be largely equivalent to the instrument that produced these data. So the HyTI spacecraft subsystems, so 6U structure. Communications, we're going to have redundant radios, so we're going to have X-band and S-band. There's also going to be a global star beacon and a global star duplex. One thing we intend to do is do onboard processing and then try and downlink rapidly not images, but subsets of information derived from images, which we hope to get down via an SMS text message. So this is something we want to demonstrate. Command and data handling. We have a spacecraft computer, which is going to do just a regular type 6U CubeSat housekeeping type work. But then, as I said, we acquire a lot of data with this interferometer, and we simply have to process it on board. So for that, we're going to be using the Univac Deep Delphi computer, which will allow us, this is our payload processor, which will allow us to process the data from the level 0 frames to the level 1 radiance product in relatively short order. ADCS, we use the CubeSpace ADCS, star trackers, reaction wheels, magnetometers, etc., etc. For the EPS, we have a 76 watt-hour battery, 4 solar panels, which have a peak generation of 40 watts. And then finally, the IDCA, which I've shown before, and the TRLs are just mentioned on this slide. So, a day in the life of HyTI. Our main mission is going to be trying to acquire data over CONUS. We are going to downlink that data via ground receiving stations in New Zealand, Spain, and then also Chile using the CubeSat network. In a month, we get about 256 CONUS passes. A month is our nominal HyTI mission duration. So basically, we're going to be sun soaking to try and generate as much power we can and charge the batteries when we're not over North America. We're going to salute to nadir, level 0 data collection, calibrate based on lookup tables which are preloaded, and also intermittent space and deep space and lunar scans to give us some calibration and validation. And then downlink the payload data to the CubeSat ground stations and then repeat that process. So although our mission is going to be CONUS, that doesn't mean we can't pursue targets of opportunity, and we certainly will. So the power budget. So a couple of main concerns when we've been going through the mission design was obviously we have a very capable computer, and we have a small refrigerator in terms of the cryocooler. So power consumption was an issue. On the left-hand side is just if we tried to do everything in a single take, this is what power requirements would look like. So you can see that the peak power consumption comes largely from the cryocooler. We then also have spikes associated when we turn the FPGAs on to do all the Fourier processing of the level 0 data. We also have spikes when we turn the radios on. But we're not going to do everything in a single orbit. So we're not going to acquire data, process data, download data in a single orbit, because that would be rather a challenge. Rather, we're going to stagger this throughout the day, acquire data on some orbits, process data on other orbits, download data whenever we can. So on the left-hand side is what it would look like if we tried to do it all in a single period of time, which we're not going to do. On the right-hand side is our nominal mission schedule, which is power generation at 40 watts, power consumption. So you can see there were 6 imaging events there with 5 downlinks, and then battery capacity, assuming our 76 watt-hour battery capacity with some efficiency reduction, taking it down somewhat below that, but basically our calculations indicate that we won't get to a significantly large decrease in battery capacity, as you can see there, by executing this type of operation scenario. So thermal control was another issue. So we have an IDCA. We have to reject heat in order to get this refrigerator working. Our thermal modeling indicates that basically when we turn the IDCA on, so on the lower right-hand side, when we turn the IDCA on and acquire data, it adds about 20 degrees to the temperature of the heat rejection temperature. Okay, so the temperature of the warm part of the expander tip at the back, and we have to extract that. So we're going to do that using heat straps and radiators on the exterior of the spacecraft. But just looking at the lower right-hand figure, basically we can use the instrument for most periods during the orbit. The dashed horizontal line is if the temperature of the heat rejection temperature is 40, then the cooler can't work hard enough to actually reject the heat. So basically we can acquire data on most parts of the orbit, but there might be some where we're close to our threshold requirement for actually using the cryocooler. So in summary, HyTI will space validate innovative new technologies to provide Earth scientists with high spatial and spectral resolution thermal infrared data from the 6U CubeSat. In terms of status, we're going to deliver by the end of March 2021 for launch to the ISS in the fall of 2021. Much of the hardware is now in-house, and we are beginning integration and test. So just acknowledgements. This is funded by NASA's Earth Science Technology Office Invest Program, and I want to thank the program manager, Sachi Babu, and then also all our co-Is and collaborators, Paul Lucy, Miguel Nunes, Luke Flynn, Saraf Pala, and his group, Don, Dave Tring, Alex Sabel, Lloyd French, Carl O'Connell, Dan and Bob Ayres, Tom George at Sereniasat, and then the group at New England Optical Systems, Pete, Greg and his team. Okay. Thank you very much.